Welcome to Coffee Break. I'm your host, Dana Curtis, and this is episode 3 of season 15. Here at Coffee Break, we invite you to join us as we dive into the fascinating world of all things microchip technology and about the time it takes to enjoy a cup of coffee. For those of you joining us for the first time, Coffee Break is a live broadcast, so let's take it over to Aliyah Fahout for some housekeeping items. Aliyah, what do you got for us?
Thanks, Dana. Hi, everyone. Thank you for joining us today. We are currently live on YouTube, Facebook, and LinkedIn, and we invite you to participate in today's episode by leaving your questions and comments in the chat, or you can email us at livestream@microchip.com after this broadcast. If you're watching us on YouTube, make sure to subscribe to our channel and click the bell so you know when we're live and when our next episode is. If you're watching us on LinkedIn, make sure to subscribe to the event so you can get all the information related to this episode. Back to you, Dana.
Thanks, Aliyah. Today we have a very special guest joining us, Robert Proctor, Technical Applications Manager here at Microchip Technology, returning to Coffee Break to talk about a new solution for maximizing EEPROM reliability. Welcome back, Bob.
Thank you very much. It's good to be here again.
Let's start with the obvious question. Why are EEPROMs unreliable?
You know, they're pretty reliable, but sometimes, they're just not reliable enough for some people.
Right.
Typically, EEPROMs have been more reliable than any other memory technology that's out there.
Right.
Flash and, rotating magnetic fields and everything else. So they're very reliable. But, when we spec them for like 1 million erase write cycles, sometimes people need more. So they're looking for more. They're looking for something else.
200 years of reliability isn't enough.
200 years of data is good. So what's the problem? I want to make sure that my great-great-grandkids can read this data. So yeah, we've been doing them a long time, and they're very reliable. So one of the issues is just making sure we keep it that way.
Right. So as EEPROM technology continues to shrink, what are some of the biggest challenges that chip makers and firmware engineers face for reliability?
Okay, so why do we shrink?
Right.
We shrink because we need to make sure that we can move our production from today into the future, into tomorrow, so that we can continue making the products that our customers want and customers need, but we can do it with modern fabs, modern equipment, and everything else. If we kept things in the old ways, eventually those become less capable. We can't produce as many parts. Things may break, things may fall away or whatever. So you kind of have to push things forward as you move along. And die shrinks are part of that. Now with die shrinks, what we're also trying to do is make the die smaller per unit memory, which means that we can make packages smaller. So customers are always asking for smaller packages.
More space on the board.
Yeah, so they want to make smaller devices, handheld devices, implantable devices, whatever. So they need smaller packages. So they need to be able to get a certain memory size into one of those tinier packages. And as far as we're concerned, we have to make sure that we shrink our processes, that we can still do everything that we put in our specs. We can still provide the millions of write cycles, we can still provide the hundreds of years of retention, and we can still provide all the erase, write, voltage range, all that stuff. So the challenge is upon us to make sure our processes can support the specs that we used to have into products that are shrunk. And so, yeah, it's not easy.
So that gets us to things like error correction codes. So how do techniques like error correction codes and wear leveling help mitigate these issues?
Okay, so we do try to make sure that we have all the reliability, right? So we can still produce millions of erase write cycles.
Right.
But the memory cells are getting smaller. And for users, oftentimes what they want is more erase write cycles, right? Now, for the 30 years we've been doing these things, we have been guaranteeing 1 million erase write cycles, and doing that as a very conservative spec. So that under these rough conditions, let's say at elevated temperature, a particular voltage, that you're pretty much 100% gonna get that. But in real life, you're very likely to get a lot more than that if you pushed it. So how do you fill the gap in between what we can guarantee and what you can actually get? It's really hard to make that prediction.
Right.
Error correction code, what that does is, it provides a way to give you an early warning to tell you that something is getting close to breaking before it breaks. So that then you really know how far you can push it, and you really know how much more endurance you can get. So instead of being limited to a million cycles, you may get many millions of cycles. And right before it starts to really lose data, you can go, okay, this was worn out, I can move on.
Right, and then that gets us into wear leveling.
Yeah, so wear leveling is important because, if you're talking about something that wears out, like the memory cells, and you're writing a particular group of bytes, let's say a status update. I need to record a timestamp and a temperature. I need to record the angles of this particular robot before it is shut down so that when it wakes up, it knows exactly where it is. I need to know what the radio stations are in the radio before I turn off the ignition so that when it wakes up, it has those same radio station. I need to know what my latitude and longitude is before I shut down so when I wake up, it's faster to lock into the new GPS position, whatever. So sometimes you need to write something, not very often, sometimes you need to write something down in the memory many times a second. So it depends on the application, but if you're writing something a lot, then that area is going to get worn out first. If you have another section of code or section of memory that you write down reference data that doesn't change, calibration data doesn't change, code snippets that don't change very often, or other stuff, they're just going to sit there and they're not going to wear. But what you're writing to most often is going to wear.
So you're getting unlevel wear on the
So it's unlevel. So how do you then figure out how to migrate those things around? I'm going to move this high loading area, these bytes, to some other place and move that low, the almost static data, and move that to somewhere else so that it's safely moved. I'm not losing any data, but then I can change the wear to a different area and then rotate that around throughout the whole array so that I generally get something that gives me a lot more endurance than just a million cycles. And I've leveled it out over the whole chip throughout this lifetime because products may last 5 years, 10 years, 20 years, maybe even 100 or 200 years if there are if they're customers that really like our parts.
That's a big range, right?
It's a huge range.
What are some of the innovative methods or technologies that are being developed to provide better insight into what a true life of an EEPROM cell is?
Okay, well, here at Microchip and where we manufacture EEPROMs, and we've been doing it a long time, we use industry standard testing techniques. We use accelerated life testing. So we take our memory, we write data to it, usually where we swap the bits high, low, high, low, high, low. And then we do that under elevated temperatures. And then we do millions of cycles. And then we we do what's called a retention bake, where we actually just turn it off, set it aside in an oven, and let that high temperature do its thing to try to help it erase data. Because elevated temperatures are very hard on everything. Right?
So talking about industrial and automotive applications.
Yeah, so what we do is we do lots of testing over a wide range of temperatures, and we take a bunch of statistical data.
Right.
The data allows us to produce a model of this memory and its logic and how the retention is withheld so that we can then, with confidence, even though we haven't been making EEPROMs for 200 years, we can confidently say, yeah, this will handle easily a million cycles and it will store its data for 200 years. So we have that in the formulas, and we've been able to prove it over and over again that it works well. So that's what we use to allow us to have confidence in our parts and give our customers confidence in our reliability.
So we've been doing this for a long time now, decades, right? It's a pretty stable technology. It's very reliable. But for EEs out there that may not be thinking about EEPROMs, what are some practical examples of how gaining more visibility into control over the EEPROM, how will that benefit their project?
Okay, so again, we mentioned that if you erase write to a particular page, byte, or whatever, and you do it a million times, first of all, are you counting the cycles? Are you keeping track of how often you're doing it? Are you using up space somewhere else in the EEPROM where you have a rolling counter. It says, well, every thousandth time I write to that, I'm going to increment that counter. And I know that when that counter reaches 1,000, that I've got 1,000,000 cycles in that area. And then what do? Are you going to say, well, I've got 1,000,000, I don't want to push the spec, I'm just going to stop and move somewhere else? Does that really help? We say, that's great, and that may be what you had, 10 years ago, but we've got ECC now. So what that gives you, it gives you the visibility to find out when there actually is an error. It fixes the error, but it gives you a flag that says, I found an error, and here's a flag. Now is a good time to start worrying about rotating the part. Instead of counting to 1,000,000 and just wondering, now you may be able to get 5, 10 million, and then, okay, now I got a lot more lifetime out of this. It's outside the guaranteed range, but it's still within the working range. And the ECC helps you extend farther into the working range of the memory reliability.
Well before failure, right?
Well, in this case, yeah, the first bit that fails, you'll get that flag. And that is fixable. The ECC actually corrects it. So you haven't lost any data yet, but you already know that you're right there on the edge.
Right, so speaking of on the edge, before we went live, we were talking about popcorn.
Yes.
How does popcorn fall into this kind of analogy we're working with here?
It's a beautiful analogy, because if you imagine you got a pan, you're going to make popcorn on the stove, the old-fashioned way. You take your pan, you put it on the fire, you put some oil in there, and you throw in a few hundred popcorn kernels.
Right.
Now, if you had like a glass cover and you're watching it, who can make a prediction about when is the first kernel's going to pop and which one is going to pop? Can anybody make that prediction? You've got hundreds of kernels, you've applied the heat, you've got an ambient temperature, the corn was in the jar for so many weeks, there's so much moisture content, you got all these variables and you have no idea.
And that's even if you're looking at it.
If you're looking at it, it's like, well, let's see, the fire is underneath this edge, so it's kind of a ring, and so you can kind of like try to guess which kernel's going to pop first, but you can't. There's no way to know.
Never really know.
But one thing you do know, when the first kernel pops, very quickly, another kernel is going to pop, and then you're going to get this pop, 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 and they're just going to, a big bell curve about, a bunch of them are going to pop, and then it's going to taper off. So you're going to get this statistical response. Pop, 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 pop. And it's exactly the same way with memory cells. If you're hitting a group of bits, and in this case, you have to work with the number of bits that you're writing to. So if you're only writing to 1 byte, you know that there's going to be a bit that'll fail eventually in that 1 byte. But in this case, if you're writing to a page or something like that, it's a lot harder to figure out which one's going to fail. If you don't have error correction code or some flag to tell you that there's a problem, you're going to have to use something like a CRC or whatever to determine that there's a failure, and that may end up not giving you enough information to fix it. So you might have to go, oh, shoot, I'm going to have to go back to an older copy of my data, or I'm going to have to keep duplicate copies of my data, or you might have to implement your own error correction. So by putting the error correction code in our chip, we've done a lot of that work for you. It gets a lot closer to having the most endurance and the most reliable data.
Protects you from the cascade effect, right?
Yes.
All right, so what advice would you give to an electrical engineer who's working with EEPROMs in their designs? Are there any best practices, key considerations? What should they keep in mind to maximize the reliability and lifespan of an EEPROM?
Okay, so when it comes to the memory devices with ECC, right, there's a very important thing to consider. We take 32 bits, which is a word, 4 bytes, and we calculate 6 bits as ECC bits. And that data is then used to do the error check and correction on the 4 bytes. What that means is, in the parts that have ECC, you have to be aware that anytime you write to one of those bytes, you're writing to all 4 bytes. So we have to, when you start writing to the one of those bytes, it reads out the whole word, it writes that new data to the new byte, and if you're done, it just writes it back in as a word of 4 bytes, 32 bits. So the ECC parts specifically have this granularity of 4 bytes. And so that's an important thing to know. You want to use that to your advantage. So always try to stay within those boundaries, 4-byte boundaries. And if you need more, work with it on the edges that are on those same boundaries so that you don't overlap into other words. So that's probably the biggest thing right there. The other thing is when you use the error correction coding, it's something that's encoded in, EC bits are encoded during the write. And the error correction is applied during the read. And when you read it out, if anywhere in your read, and that could be a byte, it could be a word, it can be a page, it can be multiple pages. It doesn't matter what size your read is. Whenever you're reading that data, anywhere during that read, if there's an error correction bit, error correction active, it will set a flag, the ECS bit that says an error correction status. It goes 1, says I have corrected something in here. And then you have to go, oh, okay, well, where is it? And you can narrow it down to individual words to figure out which word is a problem. But if it's something that you're writing to this area about the same amount of time, then you can pretty much know that it's going to start the popcorn bell curve pretty soon. And everything's going to start failing in that if you're writing to all of them at the same rate. So you better start moving stuff to a different area in order to avoid a problem. So the other thing you got to remember as a user is that you have to have room to move. So you got to get a part that's bigger than what you need. 2 times.
Built-in flexibility.
Yeah, so you got this section is what I have high endurance on. You got to move that to some other part. And if you have crowding where you got all this other slowly changing data, you might have to swap. And so doing all the swapping and stuff may require you to have buffer zones where you can have duplicate copies before you move something else in to take the place of another one. So the basic idea there is have a part that's big enough to allow you to move the stuff around and to take advantage of the ECC and to get that basically super reliability. I mean, we're talking hundreds of millions of cycles instead of 1.
Good advice. With that, let's get over to Aaliyah to see what kinds of questions we're getting from the interwebs. Aaliyah?
Awesome. Let's start with a question from LinkedIn. This is coming from Eric Moser. How hard is it to get engineering support from Microchip if we want to design an EEPROM?
I didn't quite get that.
I'll ask it again. How hard is it to get engineering support from Microchip if we want to design an EEPROM?
Ooh,
Okay.
Engineering support.
Yeah. So first of all, around the world, around the country, around many countries, around the world, Microchip does have electronic sales engineers, FAEs, that can support support product development directly. We also have application notes on our website, lots of things to read to talk about EEPROMs. And we have software tools in our development software that allows you to have not just sample code, but you can generate code that can talk to different size EEPROMs. Now, our EEPROMs are either I2C, which is the most popular interface for EEPROMs. SPI is also pretty popular. And also there's microwire, and there's a couple others, single wire. There's SWI single wire, and there's Unio. So those are like low pin count, super low pin count devices. So there are examples of all of those usage on our website, and all of our microcontrollers have support for I2C and SPI in hardware, so the peripherals are there. Fortunately, because memory EEPROMs have been around forever, there is a billion examples. And even under OSs like Linux and stuff, there's drivers and things that have been out there forever, and you just have to kind of scale them to fit whatever EEPROM that you're looking at. The data sheets are very good if you want to look at the nitty-gritty for particular bytes and how particular bits are working. But there is actually a lot of infrastructure out there in the tools to help you talk to various EEPROM devices.
Okay.
Awesome. Thank you, Bob. Here is another question from Eric on YouTube. Is there example code available for using the new Microchip EEPROM?
So the new EEPROMs, what we're talking about is the CS series, like the 24CS XX and the 25 series XX. 24 stands for the I2C devices, and 25 is for SPI devices. These devices are pretty new. There is not as much example code. So in those cases, you can still use them just like the older devices. You still, address them with your control byte, your address bytes, writing your data, reading your data. That kind of stuff is the same, but there are extra registers that you can now get into. So with SPI, you have extra commands. These commands allow you to get into these extra registers and things to do these special functions, like reading the status bit of the ECS functions to know that it's wearing out. If you can do the regular memory reads and writes into the chip, then you can do the special functions. It's the same thing, except it's a different address. It's a different control byte or different address byte. So it's just an extension of what you already know, basically. Now the datasheet is a really good place to go, because the datasheet shows you not only how to get all these control functions, but it also talks about all the other features we put in the CS devices. They're really pretty jam-packed with features, including memory partition registers. So you can actually have a software-defined write protection instead of just like whole chip protection when you set this pin or not, or half chip protection. Now you can actually say, well, this part I want to protect, this part is open, this part I want to protect, and you can have all these different, modes of protection to the part. So they're really pretty fancy. But if you don't want to use them, just ignore them. The CS devices are larger devices. So we're not going to put all these super extra features in the little teeny tiny 128-bit parts, right? We're going to put it into our 1 megabit, 2 megabit, 512 kilobit. These bigger parts where it makes sense to be able to have partitions. And so, yeah, so
Back to that flexibility you were talking about.
So again, look for those if you need it. Otherwise, if you don't need all these special features, we've still got all the other ones still there. The simpler, smaller, cheaper, whatever, we still got them.
Yeah, we've probably got it.
Thanks, Bob. Those are all the questions I have for you today. And for the audience, if you have additional questions or comments, please email us at livestream@microchip.com after this episode. And don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you, Dana.
Thanks, Aaliyah. That's all the time we have for today. Special thanks to Bob for sharing his knowledge and passion with us today. If you'd like more Coffee Break, head over to microchip.com/coffee break and click on the subscribe button to get updates for all things Coffee Break. You can also see upcoming episodes for Season 15. And of course, be sure to join us next time on Coffee Break as we explore our comprehensive power solutions portfolio with Pick Your Power. Until then, stay curious, stay creative, and stay caffeinated.